Hello and welcome everybody to this talk where I'm presenting the paper New Developments for Robot Assisting Novice Users Even Better in Do-It-Yourself Projects. As you can see from the slide, this was a joint work of a lot of people, notably people from University and Robert Bosch GmbH. In this paper, we consider do-it-yourself projects where a user wants to construct some small household object. As an example, you can consider this wooden key rack here. Such projects tend to be quite complicated and usually involve a lot of steps. For this wooden key rack, as an example, you would first have to prepare your saw by inserting a saw blade into it, then attach a battery to the saw, use the saw to saw the plank into two parts. Then you need to prepare your drill. Use the drill to connect the two wooden pieces, and then prepare drill holes at the bottom of the key rack so that you can add the hanger screws. For a novice user, these steps might be too complicated to perform, either based on the inherent complexity of each step, or because it is difficult to coordinate all the steps and perform them in the correct order and not leave out any of the necessary steps. And this is where planning comes into play, because you can use a once generated plan to tell the user what to do. So how does this look like as a general idea? Well, the user comes to the assistant, tells him what he or she wants to construct. Then the assistant will find a plan for that construction and then guides the user through executing this plan, where every action in the plan actually will correspond to something that the user has to do in order to finish the project. This is precisely what the assistant robot that we developed actually does. So now let's have a look at how the assistance provided by robot actually looks like. We present the plan in form of a slideshow where every action of the plan corresponds to one slide. For every action, we can provide a textual description of what the user should do, an image of the action, and we can provide a video for the action which instructs the user on how to perform the specific action. Further, Robot can interact with speech and touch with the user. We can use the HDN structure of the domain that we are using to provide suitable abstractions, as you can see here on the top. So we can tell him, well, you're in the first of 4 parts of the project, and within that part you're in step 3 of 6 in this case. We can allow changes to the plan, and this is something you can't see on this image here. We can proactively assist the user using the concept of so-called connected tools. To achieve all of this, Robot comprises several components that interact with each other to provide the assistance as described here. Robot contains an HDN planner, which is responsible for actually generating the plans that are used to instruct the user. We are using an ontology manager to handle background knowledge, like factual knowledge about devices. This component also intensively interacts with the planner because the planner needs some of the ontology information. We are also using the ontology to determine which texts, videos, and images we are presenting to the user when instructing him to perform a specific action. This allows us to select a best fitting text, video, or image if we don't have the perfect one at hand. Thirdly, Robot also contains a dialogue manager, which is responsible for interacting with the user, mediating the dialogue between the user and the system. It receives the inputs from the user and based on them determines which component of Robot is best suited to serve these requests, transmits the request to the respective components, waits the answer, and presents the result again to the user. Lastly, Robot of course also contains a graphical user interface. In this paper, we've described 2 important new abilities that we've added to Robot. I'll start with the ability to change plans. The reason to do so is that the user actually might not like the plan that we've generated. So for example, Robot might have come up with a plan that contains using an electric saw to saw a piece of wood, but the user actually might fear to use such a device. Instead, the user would like to use a manual saw. The problem here is that, of course, we can't know this in beforehand. So we actually have to react to the user's wishes whenever the dialog component receives a request from the user that it classifies as a request to change the plan. This request is then sent on to the planner. Such a request could look like this. The user telling the system, I want to use the manual saw instead of the electric one. We then need a way to represent them uniformly inside of the planner, and for that we chose formula in linear temporal logic. We use a neural network to determine the type of LTL formula that corresponds to the user's request, and then another neural network to determine the individual components of that LTL formula. In our example here, we might derive the following formula, saying that globally, meaning for the whole plan, we don't see the action saw electric, and eventually, meaning at some point in the plan, we will see the action saw manually. Now, once we've generated this formula, we'll run the planner again, and this time we'll not only provide it with a planning problem, but also with the LTL formula. So we'll now tasking the planner to find a plan that both reaches the goal and satisfy the LTL formula. Now, this can of course happen repeatedly, meaning the user can request multiple changes to the plan, and we just memorize a set of LTL formulas that the user has requested and try to satisfy all of them. Now, this can actually lead to problems, namely inconsistencies that can occur if the set of LTL formulas together are inconsistent. What we'll do in this case is we'll just drop the oldest of the formula first until we've reached a subset of the LTL formulas that is actually satisfiable with respect to the planning problem. The second ability that we added to Robot is proactivity based on a connected tool. Here you can see a typical drill driver. It's produced by Bosch. It's a PSR 18 Li. And what makes the tool connected is that we added sensors to it, namely gyroscopic sensors, accelerometric sensors, and a compass, which allows us to determine the actual current state that the device is in. And we do this by using a neural network that we trained with data from 12 test subjects, and the neural network outputs a classification of the current state that the device is in, which is one of these 6 classes here. So the device can either be off, it can be screwing, drilling, we can currently be changing the drill bit in front, we can currently be changing the battery, or we can be in another state. Using this data, we kind of actually know what the user currently is doing with the device. And with that, we can help the user to complete his project more successfully using suitable dialogue strategy. The first technique that we are using is, of course, to inform the user that he's actually using a connected tool. The dialogue looks like this, that Robert says, "You seem to be working with the connected tool for the first time. Don't worry, I'll guide you through the steps." Then in some situations, we'll ask supportive questions. Things like, "I noticed that you were drilling. Did that work?" The user answering, "No, it didn't." If it says yes, then Robert will just say, "Okay, fine." In this case, Robert answers, "Okay, do you need additional help?" The user says, "Yes, please." And Robert says, "A video of this project step could help. I'm going to play it for you." And then it starts playing the video automatically. Robot will also handle inactivity when it detects that the user isn't doing anything. Then Robot will say something like, "I haven't seen any tool activity by you in 3 minutes. Do you need help?" And then it starts a dialogue with the user. We of course also evaluated the 2 new abilities that Robot provides. For proactivity, we did an A/B test with 32 subjects in total, evenly split. The subjects were all asked to construct a 1 keyreg using the assistant Robot. For testing whether changing the plan works, we in a prior questionnaire determined whether they want to use an electric saw or not, and what a Robot did during the experiment was always the opposite of what the user actually liked. The system was set up in such a way that the user couldn't suspect that Robot was doing this intentionally. Now the results looked as follows. The overall verdict of the system was a bit better with proactivity, 3.38 out of 5 versus 3.14 out of 5, but this was not significantly, sadly. In total, 19 of the 32 subjects used the feature to change the plan, and the change of the plan was actually performed according to the expectations. This received a score of 4.29 out of 5. So in total, the evaluation was quite positive for us, and we think that the techniques that we've developed actually provide useful assistance to novice users in do-it-yourself projects. Thank you for your attention.